So this is a very interesting question on how we can have exploding gradient problem when we have sigmoidal units, right? So if you look at our sigmoidal unit, right, this is the blue line here is the sigmoid line, is the sigmoid plot. If this is your z, right, this plot here is sigmoid of z, right? This blue line is sigmoid of z, and this purple line here, this line here is the derivative of sigmoid of z with respect to z. Let's just write it as sigma dash, right? So this is basically a sigmoid, or we can write it as sigma dash of z. Okay, to represent that it is derivative of sigma of z with respect to z, right? So if you notice, right, your sigma dash z, or the derivative of sigma with respect to z, lies between, it can be 0. Look at the y-axis here. The maximum value it can take is 0.25. The minimum value it can take is 0. So this sigma dash z lies between 0 and 0.25, right? Now given this, we understand how this could contribute to your vanishing gradient problem. So vanishing gradient is very, very simple, because if you multiply lots of these gradients which are less than 1 many, many times, the overall value will become very small, creating the vanishing gradient problem. But the question here is very interesting. How can we have an exploding gradient problem? Because for exploding gradient, we need the gradients to be greater than 1. So let me construct an example to make this clear to you, right? So I'll construct just a very simple multi-layered perceptron. Let's assume I have my input, which is x, right? And I'll just draw one path just for simplicity, right? So I have a sigmoidal activation unit. Of course, let's assume it has weights W1, right? And this input that goes into it, let's call it Z1, right? The output that it generates, let's call it O1, which goes into the second sigmoidal unit. Again, there are weights 2 here, right? And the input here is Z2. The output here is O2. Again, I have weights 3. I have my Z3 that goes in, again a sigmoidal unit, right? I get my output 4, right? Simple again, nothing very fancy, right? I just have an input followed by O1, O2, sorry, this will be O3, not O4, I'm sorry, right? This will be O3, right? Let's assume I have one more sigmoidal unit, again weights W4, input is Z4, the output is, let's say, O4, which goes into, let's say, a loss function. And I'm just looking at one path. Again, here I'm constructing an example. Note that here I'm constructing an example to showcase how exploding gradient problem could happen even with sigmoidal units. I'm just constructing an example, okay, to prove to you that exploding gradients can happen in some certain situations. I'll construct such a situation here, right? Now it's very, very simple, right? What is my O1? My O1 is sigmoid of Z1, right? And what is my Z1? My Z1 is W1 into X, right? Let's assume there are also biases to each of these activation units. Remember, my activation unit, right? My activation unit is on Z, and Z we typically write it as W dot X. But we can also add a bias term, which we often ignore, but let's add it here just for simplicity, right? So I'm adding my B1 here. So there is also a bias term here. In addition to weights, there is also bias. In addition to these weights, there is also a bias. In addition to these weights, there is a bias. In addition to these weights, there is a bias, right? Similarly, now we can write O2 as sigma of Z2. And of course, Z2 is W2. What is Z2 here? It's W2O1 plus B2, right? Similarly, you can write O3 as O3 is the output here, which is sigmoid of Z3. And what is Z3 here? Z3 is the input that goes into this network. So Z3 is W3O2 plus B3. Okay, and so on and so forth, obviously, right? Now let's go into some more very interesting thing. Now if I want to update my W1, right? What is my derivative of L with respect to W1? I need to use this derivative, right, in the update equation of W1, right? As we have seen in your backpropagation algorithm. How do you compute derivative of L with respect to W1? It is nothing but derivative of L, right? Your L depends on O4, right? Now your O4 depends on O3, right? So on so forth. I can write this equation like this. Derivative of O2 by O1 and derivative of O1 with respect to W1, right? Because O1 is impacted by W1, right? Because O1 is impacted by Z1 and Z1 is nothing but is impacted by W1. So this is how I compute. This is again my simple chain rule, right? This is the simple chain rule that we use in the backpropagation algorithm, right? So now let's go and write this again here. Derivative of L with respect to W1 is equal to derivative of L with respect to O4, derivative of O4 with respect to O3, derivative of O3 with respect to O2. I'm just rewriting the same thing here, right? O1, derivative of O1 with respect to W1, right? Now let's look at the parts here. This derivative is dependent on the loss, right? This will depend a lot on the input. Now there are three other derivatives here, right? Remember, if you look at this network, right? This network is basically has four hidden layers. It has four hidden layers, right? The four layers that you have, right? And you have these three partial derivatives in between your input. This is your input derivative. This is your loss derivative. There are three derivatives in between. Now imagine if each of these derivatives, if, that's a big if there, if each of these derivatives is greater than 1, if each of these derivatives is greater than 1, multiplying numbers which are greater than 1 will create your exploding gradient problem. At the end of the day, that's what is your exploding gradient problem, right? If each of these derivatives is greater than 1, then you will run into the exploding gradient problem. You'll run into the exploding gradient problem. Now let's assume this gradient is, let's say, 50. This gradient is, let's say, 20. This gradient is, let's say, 10. When you multiply these three gradients, the final value has become fairly large, isn't it? Now let's look at the whole world from the perspective of just this gradient. Let's see how this single gradient can be greater than 1. Let's understand that so that things are clearer to us. So let's take derivative of O2 with respect to O1. Let's write it down. What is derivative of O2 with respect to O1? It is nothing but derivative of O2 with respect to Z2, because if you look here, O2 is a function of Z2, right? And Z2 is a function of O1, right? So derivative of Z2 with respect to O1. This is again simple chain rule, nothing very fancy here. I'm just applying chain rule here, right? And this derivative of O2 with respect to Z2 and derivative of Z2 with respect to O1. What is this? This is nothing but derivative of sigmoid of Z2 by derivative of Z2, right? And what is derivative of Z2 with respect to O1? What is Z2 here? If you look at the formula here, Z2 is W2O1 B2. W2O1 plus B2 with respect to O1, right? Now what is this equivalent to? Let's write this down. This is nothing but, okay, let's change the color here slightly. So this derivative, this we can write it as, if you recall, what did we write the derivative of sigmoid of Z with respect to Z? Sigma dash Z, right? So we'll just use the same notation. So this first part can be written as sigma dash of Z2 multiplied by, what is the derivative of this with respect to O1? So O1 is multiplied here by W2. So the derivative of that will be W2, and B2 here is not a function of O1. So you'll get nothing there, right? So this is your overall derivative that you got, right? So let me just write it. Derivative of O2 with respect to O1 was the derivative of the sigmoid function with respect to Z2 multiplied by W2, right? Very simple. Now comes the fun part. Now we want to prove that this can be greater than 1. That's what we want to prove, which means we want to prove that this can be greater than 1, or the product of these two can be greater than 1. Now let's look at this, right? We know from this we know that this derivative lies between 0 and 0.25. So we know that this derivative lies between 0 and 0.25. So this is never greater than equal to 1. But this can be greater than 1. because this is just a weight. So I can initialize my weights and biases, my weights and biases to any value I choose, to any value I choose, right? So what if, so let me construct an example. This is the example that I was talking to you about, right? What if my W2 was equal to 100? Let, if my W2 is equal to 100, okay, and if my, what is Z2 here? Remember, derivative of Z2, this derivative, this part, this can be very close to 0, or it can be at most 0.25. If this derivative is very, very small, when I multiply it with 100, so let's say W2 is 100, right? So if I multiply, if this derivative, if this, so this is 100 here, if this derivative is, let's say, 0.0001, right? This derivative is now less than 1, but I want to construct an example where this is greater than 1. So I want to ensure that this part, because it's a product of two parts, I've assigned my W2 to a large number. If I assign my B2, let's assume I assign my B2, because what is Z2? Remember, let's not forget the equation for Z2. My Z2 is equal to W2O1 plus B2. That's what my Z2 is, right? And this maxima, this 0.25 value will occur. Look at this. This 0.25 value will occur when Z equals to 0. So the derivative of Z2 at Z2 equals to 0 is equal to 0.25. Right? The derivative of the sigmoid function at 0. That's what I mean. At 0, the derivative of the sigmoid function at 0 is equal to 0.25. Now, if I make my B2, equivalent to minus W2O1, if I make it this way, then what is my Z2? My Z2 equals to W2O1 plus B2. If my B2 is initialized, because I can initialize both my weights and biases to any value I want, right? So if I initialize my weight to W0, W2, my weight W2, if I initialize my bias to minus W2O1, right, minus W2O1, then my Z2 becomes 0. When my Z2 becomes 0, I know that the derivative of Z2, my derivative of sigmoid of Z2 at Z2 equals to 0 is 0.25. So in this product, this value is 100 here and this value is 0.25. The overall product is now 25, which is greater than 1. Here you might ask that you are force fitting the initialization. Yes, I'm trying to see, as I told you at the start itself, I'm trying to construct an example where these individual derivatives can be greater than 1. Even if one such instance occurs, right? See, this derivative now can be greater than 1 if I initialize my W2 to a large value like 100, and if I initialize my B2 to be negative of W2O1 such that my Z2 becomes 0 and the derivative of my sigmoid function with respect to Z2 is 0.25. Now, given this initialization, because remember, when I train a deep neural network, I can initialize my biases and weights to whatever value I want. With this specific initialization, like this is like a proof by counter example. Here I'm trying to construct an example where this derivative can be greater than 1. And when it is greater than 1, when this, just the way this derivative can be greater than 1, I can construct an example where this derivative also will be greater than 1. And this derivative also will be greater than 1. So imagine if this derivative is 25, this derivative is 25, and this derivative is also 25. You are multiplying three extremely large values. Okay, and the overall derivative of the loss with respect to W1 has simply exploded. It has become very, very large now, isn't it? So you can have instances even with sigmoidal units, even though the sigmoidal unit doesn't have a derivative which is greater than 0.25, you can still construct examples where you will encounter exploding gradients because of the way, this is very important, because of the way you have initialized your weights and your biases. You can construct counterexamples like this wherein you can observe exploding gradient problems. And exploding gradient problems often occur when the depth of this is very, very large. And that happens a lot in recurrent neural networks that we'll discuss later in this chapters. So there's a whole chapter called recurrent neural network, wherein the depth of these networks is going to be very, very deep. And we use recurrent neural networks primarily for time series processing. We'll come to all of those details later. But such a problem can exist, and it does occur actually in practice. I just wanted to show an example here, or construct an example to showcase to you that it can happen based on how we initialize our weights. Of course, the example I've picked here is an extreme example. But for exploding gradient to happen, this value need not be 25. Even if it is like 1.2 here, this is 1.1, let's say, this is 1.4. If I have many such values, if I have many such derivatives, or if the depth of this network is, instead of 4 layers, if it's 40 layers, which happens a lot in RNNs, right? You can have exploding gradient. That's one. I'm just constructing an example here, right? Of course, I've constructed an extreme example as I told you, but things like this do happen in practice.